Suppose R is a relation from A to B, S is a relation from B to C, and before we even talk about the other stuff, let's try and draw a picture that we can look at. So we have one set A, another set B, and a third set C. Try that again. Okay, and we have a relation R from A to B and a relation S from B to C. Okay, we're not assuming these are functions, they're just relations, right? They're subsets of the Cartesian product of A and B for R and B and C for S. Okay, and we're assuming that the range of this relation R is B and the domain of this relation S is also B. And moreover, we're looking at the composition of these two relations, which we call S composed with R. Remember, composition is defined for relations, not only for functions. And that's not only a relation from A to C, we're actually assuming that it's a function from A to C. Okay? So we're not assuming that R and S are functions, just they're relations. But we are assuming that the composition is a function, and then we're supposed to prove that in that case the function the relation S actually has to be a function too. Okay? So that S composed with R being a function implies that S is a function, basically. So let's try to understand why that is. I mean, for S to be a function, then if you have any B in a set capital B here, there has to be exactly one C over here such that BC is in S, right? So for the existence part, we can just notice that this capital B is the domain of the relation S, and so that means exactly what we want. For existence, there exists some C over here such that BC is in S. And then for uniqueness, let's see, well, suppose we have a couple elements, maybe D and E over here in C, which, such that BD is in S and BE is in S. And we want to show that actually D has to equal E, right, so that it was unique. And the things we haven't used yet are that range of R is B, and but this is a function. Okay, so because B is the range of R, that means there exists some A over here, which maps to B, right? So maybe I should say such that AB is in R, which is R related to B. And once we have that, because AB is in R and BD is in S, we know that AD is in the composition S composed with R. And similarly, because AB is in R and BE is in S, we know that AE is also in S composed with R. And now because we have AD and AE in this composition, which we're assuming is a function, right, we know that D and E must be equal to each other as desired. All right, so a lot of arrows in that picture. Hopefully that made some sense, but let's try and work out the details a little more slowly in a proof. Okay, so here are the givens. We know R and S are relations, so they're subsets of the Cartesian products. And our other two givens, and our goal is to prove that S is a function. So to be a function, well, it has to be a relation, it has to be a subset of B times C, and it has to satisfy this for all B, there exists a unique C condition. Okay. And similarly, for since we know that S composed with R is a function, we know that it's a subset of A times C, which I guess I haven't written here because we probably don't need it. And we have for all A and A, there exists a unique C condition. All right. And the nice thing is we're already assuming that S is a relation from B to C, so that goal is already taken care of. And basically we're trying to kind of upgrade that to the statement that it's a function, right? And for that we need to add on this other goal. So we'll focus our attention on that one now. And for that one we can let B be an arbitrary element of capital B and prove this there exists a unique statement. Okay. And for that, well, there's the existence part and the uniqueness part. So to think about each of those separately. Looking on the left, on the given side here, we know that B is in capital B, and we know that capital B happens to be these other two things. So from that, we can immediately conclude that little b is in those two sets. And we should think about what that means, right? For B to be in the range of R means there exists some A in A such that AB is in R. And for B to be in the domain of S means, that's exactly what we wanted, right? That there exists a C in C such that BC is in S. So that leaves us with the uniqueness as our remaining goal. So we will assume that, we'll suppose that D and E are arbitrary elements of C such that these two statements hold. Okay, and we'll try and prove that D has to then equal E. And as in our picture, we're going to use the fact that B is in the range of R, which gives us an A naught and A such that A naught B is an R. Okay. And if we, now that we have an element of capital A, we can do a universal instantiation on this statement to get that there exists a unique C in C such that A naught, comma C is in the composition of S and R. Now with that and the D and E over in C that we are given, if you write out the uniqueness part of this statement, it would say, for all D and E in the set C, well, okay, this is where I want to get to, right? It's going to say that for all D and E we have this, okay? And so what I've done after that is to do a universal instantiation with this particular D and E that we're given to make those quantifiers go away and make it fit on my screen a little bit better. So we have that conditional from the uniqueness part of that statement. And we're just about there now, because if we combine the fact that A naught B is in R with the fact that these two things are in S, then we get that A naught D and A naught E are in the composition S composed with R. And now modus ponens is exactly what we need to get our goal. All right. So here's the proof of part A. Go ahead and pause if you'd like to kind of compare your givens and goals over here to what I ended up writing. What's left is part B. Okay, you might well have wondered, we said that if the composition is a function, then the second function S, the second relation S has to be a function. You might wonder whether R has to be a function too. And the answer is no. Okay, and so part B asks us to give an example to show that it doesn't have to be the case that R is a function from A to B. And I've typed out over here my somewhat simple example, but let's draw a picture of it so we can understand it a little bit better. Okay, so we have our three sets A, B, and C. And A just has 0 in it, a single element. B has a couple elements 1 and 2, and C has an element 3. And to be finding R to be the entire Cartesian product A times B. Okay. So what does that mean? Here's R, and then S is going to be right here. That just means that it has all the ordered pairs where the first coordinate is anything from A and the second coordinate is anything from B, right? So that in this case is 2 ordered pairs, 0, 1 and 0, 2. And then similarly S is B times C, so that's going to have 1, 3 and 2, 3 in it. And okay, well, so that's my example. Now let's check that it satisfies the assumptions here. R is a relation from A to B, S is a relation from B to C, sure. Range of R is the entire set capital B, right? As is domain of S is equal to capital B. And moreover, if you look at the composition of these two functions, then all it has is the ordered pair 0, 3 in it, right? I mean, there's two different ways to get from 0 to 3, but that doesn't matter. So so that's a function for every element over here, namely just 0. There exists a unique thing over here, namely 3, such that 0, 3 is in there. Okay, so we do have that S composed with R is a function, and then I'm supposed to show that it's possible for R to not be a function, and it's not, right? We have this input 0 for which there are these two different outputs, okay, which is okay for a relation but not okay for a function. So R, which is the set of those two ordered pairs, is not a function. And we're done.